Good afternoon, everybody. So this is my great pleasure to share our research on desalination and lithium resource recovery from seawater and seawater brine. So thank you for our first host, Han Wei, was Chen co-authors from this research and discussion. So I will briefly mention about desalination. Desalination is always more important for the sustainable water resource. And brine mining was one of the new topics we like to tackle for some of the cost-effective way to recover some resource recovery. So we want to use membrane, capacity deionization. So this will have a little bit more selective lithium recovery. So I will focus on lithium. Even though we have several experience for different resources such as lithium, also magnesium and bromine. But this time, so lithium will be the main talk for today. So already you know that seawater is a reliable water and food, mineral and energy sources. So we really benefit a lot from seawater. So Australia is very lucky to have, we are surrounded by seawater. So we have utilized a lot of seafood, with some of the desalinated water, and then in the future we'd like to have more hydrogen using water electrolysis. The energy can be obtained, yet still we are using a lot of the tidal renewable energy from seawater. Also mineral can be next target we can try to benefit. Already we have a lot of benefit for table salt. So every day you are eating a lot of salt, sodium chloride. Without salt, your food is a very terrible taste. Yeah? So we got a lot of benefit from seawater minerals. So we want to go a little bit more recovery of the resource from seawater. So if you look at what is inside from our seawater, chloride, sodium, and we have also different minerals. So this is the very large concentration, but if you look at the micro concentration, so lithium 0.2 milligram per liter, aluminum also very much similar, 0.2 milligram per liter. So bromine is around 50 milligram per liter. So these are the main target we like to have a high value resource recovery from seawater. So desalination becoming more and more because we need more people to support water. So water is not only our drinking water, but entertainment, also producing a lot of food together with water, also our clothes, everything is related to water. So we have to have more water in the future. So if you look at the growth for last 10 years, you can see that SWRO is very much significantly growing this technology, and the summer is also still growing, and the BWRO. So if you see the value of the seawater desalination altogether, almost $6 billion. So this is only for the CapEx per year. So if you consider OpEx is always double of the CapEx because you need a lot of energy to produce desalinated water, as well as labor cost, chemical cost, waste cost. There are a lot of cost involved, so that the capital cost, OpEx cost altogether, so you need to think about 3 times. So you have 6 billion, the 2 times for the OpEx cost, so almost $18 billion every year we have to spend for desalination plant operation. So in the future, it's becoming more and more larger market, so that we have to think about how to reduce the energy, how to think about the valuable resource. So that's the reason why we have look at some of the brine mining opportunity. So you can see the seawater monovalent and divalent. So you can separate using nanofiltration So easily you can transfer into different magnesium or monovalent ion. So you can also separate for the multivalent using different technology. So polymer ion exchange membrane or 3D absorption, also ion liquid. So you can recover a lot of useful multivalent ion from seawater. Also you can recover monovalent ions. So lithium and rubidium, also bromine. So there are very useful material we can recover from seawater. So if you look at the value of the risk element, so you can see that this is the seawater concentration, and this is your price. So concentration, rubidium and lithium is around 0.2 milligram per liter in seawater, and the value is around $10 per 1 kilogram. And the rubidium is around $10,000 per 1 kilogram. And bromine is also high concentration, and magnesium, and then value is also very high. So our research group have developed how to recover these four main elements so that we can make another value for seawater desalination plant. So this is the currently most commercially available seawater brine schematic. So New York City, you know that in Saudi Arabia, they like to have a new generation of future city, and they need a lot of water, so that they want to build the world's largest desalination plant, 1 million cubic meter per day, and DMF, CF, and nanofiltration. The nanofiltration monovalent goes to the SWR, and then multivalent come to the membrane crystallizer, and then finally they like to produce the 2 million sodium chloride and crystal sodium chloride, also liquid sodium chloride, and bromine, as well as the lithium and rubidium. So that's their consideration. 2 million tons salt can be produced, and then they want to extract as much as possible from this salt. So how we can contribute from this project? So we have selected CDI. So CDI is the emerging desalination technology. So you need the graphite and how to activate carbon electrode water channel, and then you can just utilize direct current. Then you can separate your cations and anions. Also you can utilize the cation exchange membrane, anion exchange membrane, and then you can selectively contain your ions, so that we can have a very high selectivity using this CDI technology. And then this is also desorption. You can just utilize short circuit, reverse polarity, and energy recovery. So it can be a more energy effective process. Also, a lot of people are utilizing different electrodes. How the activated is the most cheapest one, so people are using. And then carbon material was under development for this electrode. So at this moment, the CDI, MCDI mainly utilize brackish water, water softening, heavy metal, water removal. But we like to apply this one for this resource recovery. So we have experience for last 5 years. We have contributed CDI for the low energy efficient desalination to replace second class RO. Then we have saved around 0.3 kilowatt hour per cubic meter in a desalination plant. And also we have collaborated with the UNDP to have the Tuvalu, because they are sinking for their country because of the climate change, ocean level rises. So we like to have them for the desalination using this CDI. So we are working with the UNDP, and this is the first our lithium resource recovery. So we have published. So if you need more details, so you can find it from these papers. I don't want to repeat a lot of general information on lithium, because yesterday we had a lithium workshop organized by Hamid. So a lot of people mention about lithium. Also today, our plenary speaker, Professor Wang mentioned about lithium. So everybody talking about lithium. So I'm sure that you know why we need more lithium. So just one point is land mining in lithium is 22 million tons reserve we have. And lithium in seawater, it's almost 230 billion tons. So it's a huge amount of lithium is contained in seawater. So challenge is sodium concentration, magnesium, calcium, potassium are much higher concentrations. So we need to make sure how we can selectively collect from this lithium from seawater and brine. So there are many technologies you can use. Also, we have UIO 66, GIF8, looks like a very promising material to utilize to selectively collect the lithium. This is the basic theory of your LMO, LTO, LMTO. So you can just lithium replace with the hydrogen so that you can easily observe and dissolve. So it's like the ion exchange mechanism utilized to have a selective lithium recovery. So first, our experimental result is MOVE-based electrode for selective lithium recovery from aqua solution using this MCDI. You can see that we have CDI. Then we try to cut with the GIF because GIF size with the lithium is very much similar, so that we can selectively utilize the GIF gate. And then just the lithium pass through, and we can collect only lithium from this CDI electrode. So that's our result comparison. Also, we compare with 4 different scenarios. So first, we put the electrode for the activate carbon, and then in situ growth of the GIF8, and then to avoid this wash out from GIF on the powder activate carbon. So we just coated with some of the electrode with the cation exchange polymer, and then how this will function. So this is the just the normal GIF8 on the top of the activate carbon, and this is with the cationic exchange membrane electrode. So you can see the difference of this material, and we compare just to 4 different scenarios. First is the electrode activate carbon only. Second one is the GIF on the top of the electrode, and 3 is the electrode and cationic exchange membrane, and last one is the activate carbon GIF and cation exchange membrane. So we compare with this result, and then found out that when you have only electrodes, so there is nothing much lithium selectivity compared to the other ions like sodium, potassium, magnesium, calcium. However, when you do this GIF on the top of the activate carbon, so we increase the overall selectivity up to 3.08, lithium to sodium and lithium to potassium 1.12. Then when you use the only cationic exchange membrane, so we were not able to find out any selectivity increase. But when you increase also GIF8 in between electrode and ion exchange membrane, so we slightly increase the sodium 1 to 3, potassium 1 to 1.8. So which means the GIF flow is much more important than our activate carbon and cationic exchange membrane. So based on that, so we look at some opportunity combined with the different HMO, and then we will share the result later on. And we also look at the polymer because cationic exchange membrane was not really improved the overall selectivity. So we look at the more specifically spec polymer to recover more lithium from this CDI. So we changed the cation ion chain membrane, which is spec 20. 20 means 20% of sulfonate group. So sulfonate group attached with your lithium, so that you want to capture more ion change function, so that you will have a more high concentration of sulfate functional group, which will have a more lithium combination, which means you will get more selectivity of the lithium when you have a spec 20%, 40%, 60%. Also, when you have a more sulfonate functional group, you have a more hydrophilicity. So we changed on the cation ion chain membrane, and then look at the selectivity of our lithium recovery. So you can see that we use the different spec polymers and coated with the powder activated carbon. This is 20%, 40%, and 60%. So we coated with them, and then look at the contact angle. So it becomes more hydrophilic from 85 degree to 63 degree. So we found out the hydrophilicity with the higher concentration of sulfonate group. And then we look at the activated carbon only, spec 20%, 40%, 60%. And interestingly, so selectivity leading to metals. So potassium showed very high selectivity compared to other components. Also 40% is potassium, 120%, and spec 60%, 156%. So this spec polymer, when you increase here, you can increase your overall lithium recovery. And they have specifically potassium competing ion with the lithium can have a higher selectivity compared to the other ions. And based on this result, also we look at the HMO. The GIF was a very good material to have a very high selectivity. And then we combine with our HMO on the top of the activated carbon. And then we look at the overall outcomes, how we improve this lithium recovery. So this is our result. So this is the HMO GIF material. We just mixed randomly with the activated carbon, and then we created this electrode, and then look at how this will improve the overall lithium recovery from this fabricated electrode. You can see the result, HMO and activated carbon, and then zinc dot HMO and activated carbon, and this is HMO and GIF and activated carbon. So if you see the sodium, potassium, lithium, so overall they are removable, C0. So lithium concentration, HMO is almost 0.8, 0.28, and then this is a zinc HMO, it's around 0.45, and this is the overall HMO GIF activated carbon, 0.4. So which means lithium recovery removal is better in zinc HMO, HMO GIF activated carbons electrode. So we look at those selectivity and this selectivity compared to the HMAC zinc HMO. So we found out the selectivity is around 13 for this HMO GIF activated carbon with the sodium, and then potassium is around 6, and then magnesium is around 2. Higher selectivity we achieved from this HMO and GIF material. So overall, so we look at some stability of the absorption desorption, because so if you just wondering whether this is only for the one experiment or just a short time. So we look at the 4 cycles in terms of absorption and desorption. Then we observed very much very similar pattern of the overall absorption. The sodium and lithium increased. So lithium is the highest selectivity from this one. Also, we just stopped this current, and then desorption occurred. Also, lithium desorption was very higher compared to the other ion compounds. So I can conclude our ongoing vision. The brine mining becomes more important to recover critical minerals. Also, just the simple our table salt using our brine because we want to value a desalination plant for circular economy resource recovery. And lithium can be selectively recovered using modified MCDI. And in this modified MCDI, so there are many mechanisms: electrosorption, side explosion, and then some of the Coulombic potential van der Waals play a vital role. So while this target ion possess less charge density compared to the other complete ion, so we have to look at the more fundamental aspect for this separation, and then we can also focus more on scaling up because the CDI, one of the advantages is to scaling up easily once you have a very good material on the top of your CDI. So that could be the next step we'd like to improve. And thank you for the ASC funding, discovery, also UNDP, also industry partner for Shon. Thank you for your attention.
Thanks very much for the wonderful talk, Professor Shon. Is there any question from the audience? Yes?
Thank you very much, Shon. A question on the selectivity, because CDI always had that issue of selectivity compared to the analysis of all techniques. And here we can see some improvement in some ions as you have shown. But have you done some calculations in terms of what would be the minimum or optimum selectivity for a technology to be marketable? Is that something that you have looked into?
Yeah, that's we are under investigation because it's a technical issue because still we have not achieved very high selectivity, so that we haven't done this level of because it's not about your energy apply, it doesn't mean you will get the high purity of the lithium. So we haven't really achieved that level, so that we are not sure at this moment what energy apply and what kind of energy we apply for the economically viable or not. So that could be possible when you have a more optimized purity of the lithium, which can be commercialized directly or applied directly, so that based on that we can go for the next step. But as you know, still sodium, other ions in brine and seawater, they have a lot. So our purity is, even though selectivity in this study just compare with sodium, potassium, calcium, magnesium. However, in the future, we have to look at the level of the commercially needed purity of from this seawater. So that's we want to go first, and then your answer will be maybe from next year or following year.
Is there any other question?
Thanks, Shon. Very interesting. Just a quick question regarding the volume of the brine you can process. Do you have any sort of estimation of how much brine you can process with the current modification of the CDI?
Okay, so that's a good question because CDI, as I mentioned, the scaling up is the one of the advantage. So you connect the cells, your electron cell, as many as possible. So your volume of the brine will increase. You have more absorption of the lithium or targeted ion, so that you will have a more cell, more volume. It's very much proportional. Yeah. So that depending on how much volume you need, how many cell and absorption capacity, based on that, or we can just absorption disruption. We can just make a partial batch contribution. Otherwise, if you have a very clear volume 1 cubic meter, we need just 10 cells to absorb your lithium, more than 95%, so that you can calculate based on your volume and the cell absorption capacity. So that could be easily we can have some process optimization.
Technically, one of your cells could be on the absorption and the other one could be at the same time the absorption.
Yes, like one option, this option you can have a switch and then this two module or cell. Yeah.
Thanks. Any other question? I'll have a quick one as well. So it looks like the focus of the electrode research is on improving the performance of the carbon electrode by applying some coatings and so on. I was wondering if there is any practical, yes, interesting alternative for the activated carbon itself.
Activate carbon is.
Or it's going to have to be there all the time and then we can just try to modify its performance.
In fact, okay, people are using electron activator because this is the cheapest material. Compared to the Maxim or graphene, they have more high surface area, but the production cost is much higher than this activated carbon. So that's the reason why people are using activated carbon, because of the techno-economic related issue. So this activated carbon at this moment, because the CDI itself is not really well commercialized, because the reason why the CDI is not really cost effective compared to the other technology. And then if we increase the more different electron material or modified material. But in this case, we selectively collect the specific ion, high ion, lithium, rubidium, or some other compound. So you can design, because the value of this material is higher than water and higher than any other material. So we just try to modify. But absolutely, if you just think about water, water 1 cubic meter is just $1. Yeah, $1. So if you consider modification and electron, of course, the economic analysis is not really matching one. So considering that point, so activate carbon is currently the most viable material you can use in modification for, especially resource recovery, not water. Water itself is too cheap, so this technology may be too expensive compared to water production. But when you consider rubidium and lithium, which is a high value material, will be possible to use this.
Thanks. Yeah. Thank you so much. It's been a great talk.